Hello everyone, and welcome again to Engineers Ireland. Today, in the two classes that we will have today, we're going to go through, in the first one, the geometry of the line, and in the second one, the geometry of the circle. And you will find that there are quite a number of tie-ins. That's why I'm putting one straight after the other. Now, before we start, there are two things I just want to mention to you guys. The first is, as well as dealing with Aidan's Rowntree's maths books, which are the main ones I use, I just want to bring this to your attention. Now, this is John Brennan's Past Solutions, and the new one is out at the moment. It just got into Eason's this week, so you should be able to get it in different Eason's branches, or at least order it and then have it for you in a few days. There are 11 full years of past questions in this book. But more importantly, there are 11 full years of answers to the past questions, and I'm a firm believer that using this particular book is of great value to you. I have reasons for this. Even when you have learnt your mathematics, there's still a transition you have to make, and that transition is a one to becoming a very competent answerer of questions for the Leaving Cert. Now, he lays out his book in a very good way. If I just randomly open and say to you 2001 question 1 paper 2, this is the part C bit of it. Well, actually, I'll start with another question. This one, because it's more typical, okay? 2000, question 8, higher level, paper 1. The question is here, the A, B and C is here. Sometimes, like the one we just looked at, if there's a bit too much of an answer, he'll move a bit out onto the next page. But fundamentally, how it's organised is on this side, you get the question, and over on this side you get the answer. Now, the other thing about it is, that's 2000 question 8. If I went to the previous page, I've got the 2001 question 8 with its answer beside it, and so on and so on. So there's the 2002. It never fails to amaze me how much time you can waste flicking back and over through a book of past questions if you're wanting to, for example, hunt question 5 paper 1 and you want to do quite a number of questions. He has it neatly laid out, okay? There are other reasons why he's very good. They relate to what he has in at the start. He tells you at the start all your must-knows. These are the things you must know, and it's done on a question-by-question basis. It's a very useful way to allow you revise. These are the things you have to focus on. So if you've chosen the questions that you wish to do in the exam, you can go to this and he'll tell you each of the things that you must know. Okay. Now, along with his must-knows, he also has required proofs. All the required proofs are in here. He's a very good guy because, well, at least for you doing the Leaving Cert, because he is genuinely doing his best to help you. What you will find in some questions, he has got more than one ways shown you of doing the answer. Now, I actually don't mind how you do an answer. All that matters to me is that it's the way that suits your mind and the ways your mind thinks. Clearly, if the exam question said solve using integration, well then you must use integration. But if it just says solve something, even though it's in an integration section, you don't actually have to do the integration. You can use a different method. He's good because he talks in terms of using vectors to solve certain algebra problems. All of that is allowable, provided the question didn't specifically tell you to use a particular method. How I would expect you to use this book is, to begin with, while you're still getting your feet and getting the idea as to how to answer questions, you should, for example, you're following question 5, we'll say. open it, take a look at the question on the left page. If you can solve it, or part of it, go ahead. And if you can't, look across to the right and actually see how it's done. Because many times the reason you can't solve the problem is you just haven't got your head wrapped around the idea of kind of solving Leaving Cert questions. And you can perhaps be much better than you think you are, but while you think you're not all that good at them, you won't solve them. So what will happen is, after looking at 3 or 4 years worth of question 5s, you'll start to say, there's a pattern to these, to how we answer them. And that pattern in reality is, it's a viewpoint. You develop a particular viewpoint, which is the practical usage of your mathematics, and you can get that from this book here. It's very useful. Once you get further on and you get more confident, all you can do is, with another book or an A4 sheet, cover the answer page when you turn over and attempt the question yourself. Over many years, I've actually found that students using this book perform better in the Leaving Cert. Now, let's get on to geometry. To begin with, we're going to look at geometry of the line. This is one of the really cute sections in the Leaving Cert. It's not too complex. The questions may be a little long, the answering of questions may take a bit of time, but all in all, it's a very doable one. And it's very important because the line in geometry is the kickoff for differential calculus. You will also find that there are tie-ins to complex numbers and to vectors. So, to begin with, I've mentioned before about Nicole d'Erasme, who developed graphs. But he actually didn't develop them into the Cartesian system that we have now, mainly because algebra was very poor back in the 1350s. But about a third of a millennium later, in the early 1700s, another Frenchman, Descartes, who is much more renowned for his book on philosophy called Thoughts than he is remembered for his mathematics. He's the guy who probably gets most of the credit for this. Now, interestingly enough, yet another Frenchman, Fermat, also worked on a system of combining algebra and geometry, and between them you could possibly say they should share the credit for something you've been using for years. One of the tricks in their Cartesian system is that this quadrant here has plus in the x, plus in the y, this quadrant down here is minus and minus, etc., etc. So it helps break things up, it gives a sense of direction and everything. Now, that we have just discussed that little bit, let's have a look at the first equation that's given. Now remember that the graph is the system that unifies geometry with algebra, and it has been the cause of the great revolution that we've had in mathematics in the last few hundred years. Now if we look at this, and we'll say that this lower point here is x1, y1, and the upper point is x2, y2, and we're looking for and they refer to it as the distance formula. In other words, this line between the two of them, how long is it? Well, now that we are in the advanced world of being able to unify geometry and algebra, we're able to replace a slopey line, which, believe it or not, is a complicated thing, with two simpler things, and that is a horizontal line and a vertical line. So in our graph, this location is x1, that location is x2, and the difference between them, pretty obvious stuff. And likewise, this vertical height here is y2 minus y1. The interesting thing is, you will notice immediately that that same diagram is used for slopes of lines. It's the y2 minus y1 over x2 minus x1. But here we're looking for this distance. And the important thing is we've set up a right angled triangle. As soon as you've set up a right angled triangle, you're going to, any time in your mathematics, not only for your Leaving Cert, you should always think in terms of Pythagoras. And Pythagoras tells us that the square of that length plus the square of that length is equal to the square of that length. So we're now in a nice happy position that the distance between point A and point B here, which is shown with these two vertical lines, it's equal to the square root of that length along here. Sorry, it's the square, and that one here, both squared. Okay, so here we go. All straightforward stuff. So all I'm saying to you is, it's a distance formula. It's not that, oh my goodness, I have to learn yet another formula. Once you think in terms of Pythagoras, this is absolutely obvious. It should come straight out from mathematics that you've known since second year, not even third year or fifth year, but just simple little second year stuff. The next formula that it relates, that's in here, has to do with the midpoint. You can call it M. If you look at it, what you can say is I can travel all the way out to x1, which is out to the point A horizontally. If I travelled then all the way across to the B location, I've gone as far as the x2. So the horizontal value for the M should be the average of the two, because it's halfway between the two of them. So horizontally, we're saying that location would be the x1 plus x2 over 2. The exact same reasoning applies to the average vertical height. It has to be y1 plus y2 over 2. It's just the average of the two values. Again, this is very simple mathematics, and the equation is a one that should be clear to your own simple and straightforward reasoning system. Now, this particular one here, the finding the median, or the mean position between 2 points, is a very special case of the third formula, and there's two versions to this third formula, which is the divisors. Now, the reason there's two versions what we're looking at is a situation where there's a point C and it's somewhere between A and B. This is the first case, and we're saying C will divide it in a certain ratio. We'll divide this distance between A and B in a certain ratio. And the length, this part here, is R. That part here is S. The second version of it is where C is outside. Now this is the important thing to remember, that the R is still relating to A relative to C, and the S, I drew that wrong. That's what happens when you think ahead. The S still relates to B and C. So then, what can we say? We're saying that we have a ratio. Now remember that in the alphabet A comes before B and R comes before S. But in the equation, and the easy way to remember the equation, is that the R and S just get swapped around in the equation, okay? While R may be related to A in the diagram, it's multiplying into the B in the equation. So what we have Now you will notice the pattern of this internal divisor one. The pattern is that the x bits look just like the y bits. So once you remember the x ones, you can immediately remember the y ones. Now we have the exact same pattern as before. We have x1, y1 down here at A, and we have x2, y2 up here at B. So notice S relates to the x1, even though in the diagram the S has to do with the ratio across to the B point. It's actually relating into a number that's part of the A1. Okay? So in the equation, you just remember that the S which belongs to the B in ratio is multiplied into the A, and similarly for the R1, it just swaps across. What we have also here is there's a plus. There is a plus. In total 4 of them. All the internal divisor signs are plus. The external divisors, instead of a plus, has a minus here. So in reality, all you have to remember is, if you remember the x bit for the internal divisor, once you remember that one, you can immediately set up the y bit, and you know that the external divisor, which is this lower diagram, the one where the C is outside of A and B, you know you just need minuses. Okay? Now, that's basically the only trick in knowing that. And you'll be glad to know that we're not going to continue on this same kind of style of, oh, here's an equation, here's another equation, because that gets very boring. Okay? Now we're going to start looking at something that is almost exactly the same as something covered in vectors already, and it has to do with the angle between two lines. Let's look at the lines over here. And it's custom to call or to put Greek letters. So here's theta. Theta is an angle. Now, just to be clear, an angle is a rotation. Okay? It hasn't got to do with length. It has to do with how much something is rotated. If my, sorry, for you out there, if my hand is here, and we'll say it's flat, and we'll say this is 0 degrees, 0 rotation, that gives you approximately a 45-degree rotation. That rotates it perpendicular to the horizontal, and it's 90 degrees. So the theta is just a rotation. Okay? Now, we actually, to do this little bit that we're coming through here, we just need to recognize a few little things. We need to remember what we knew from junior cert. If we had 2 points on this line, we need to know that the slope of the line is y2 minus y1 over x2 minus x1. That's pretty obvious. Okay? You've known that for years. Here's the second thing you need to know, and now you just need to dip in a little bit into trigonometry. In the same way as that basic little line drawn like that is the fundamentals of geometry of the line, the unit circle is the fundamentals for trigonometry. You will find it in the logbooks. Now, I never expect to win a prize for my quality circles, but all they have to be are visual aids. It's the unit circle because it has a radius that's just 1 unit. Okay, so the length of this radius is just 1 unit. Now, if we look at it and say that I have an angle theta here, we now just need to know what the basics of trigonometry are, and that is what's cos, what's sine. No matter where this radius is rotated around in the circle, you follow one simple instruction, and it's best to get the language right of this, okay? You go to the end, the tip of the radius, and from the tip of the radius parallel to the y-axis you draw a line towards the x-axis. So no matter where it is, any quadrant, tip of the radius, draw a line parallel to the y-axis towards the x-axis. Once we've done that, this length here, we can name it. It's cos of theta. And that length there we can also name, because that's just sine theta. These are unusual words, sine and cos, for us because they originate from India. It was the Indian subcontinent that gave us 0 and also gave us the fundamentals of trigonometry. The Greeks really didn't have a lot of success in this. Okay, so what we have are corruptions of original Indian names that made their way all the way across Arabia, off up through Spain, and in Spain Christians learnt from the Muslim masters, and we have a corruption of the original words, but we call them cos and sine, and that's fine. All that matters is that we are all sure as to what it means. Now, the interesting thing about it is the third main trigonometry one, which is tan, is sine theta over cos theta. Now, if you think about it, we're saying it's the vertical amount divided by the horizontal amount. That's exactly the same as our slope equation. Our slope equation is saying in this straight line it's the vertical amount divided by the horizontal amount. So tan is just slope. So y2 minus y1 over x2 minus x1, which is your traditional way of working out the slope of a straight line, is exactly the same as working out tan of the angle that the line makes with the horizontal x-axis and the positive side of the horizontal x-axis. So then, we're now in a position where we can say that these are the same thing, and the usual letter that's used for slope is m. So now tan theta is m, the slope of this little equation over here, and that equation is normally put in this form: y equal to mx plus c. So then, if we run the alternative form of the line equation, what we will have is ax plus by plus c equal to 0. They could tell you it's 3x plus 7y plus 5 equals 0. Now, you should always try and put it into its standard form. That's the one up here in the top right. And let's go and do that now, okay? That value, minus a over b, is the slope m. It also happens to be the tan of the angle that this line makes with the positive side of the x-axis. And just to be clear, this piece back here, the minus c over b, is where this line will hit the y-axis. And the simple proof of it is, along the y-axis, x is 0. So when I put x equal to 0 here, I find y is equal to minus c over b. But fundamentally, the bit that you really are to focus on now is the minus a over b, because that's the slope. We're leading up to a proof. This proof is a one that can be asked in the Leaving Cert. It's actually an easy proof, but it's also very easy to make a mistake in it. And the reason it's easy to make a mistake is people forget to finish it, okay? And what we want to find out is the angle between two lines. Here are two lines. This one up here with the positive slope is L2, and this one over here with the negative slope is L1. And each of them have an angle with the positive side of the x-axis. And what we want to find out is that. What's this thing here? Now, you have to see that there is also another angle between the two lines. That one. From your junior cert, you know that theta is the same as this angle across from it in the little crossroads, the same way as the one over here is the same as that one. We also know from our junior cert that all the angles on one side of the line add up to 180. So we can say that this is 180 minus theta. All ready to go then. What else do we know from junior cert mathematics? We know this little diagram. And what we know is if we have an angle here and an angle here, this angle C is equal to A plus B. All of this is just junior cert mathematics. This should not be difficult for you. So then, if we use the information from this low little triangle in our upper one, what we will find is that, we will get alpha is equal to beta plus theta. So we have an expression for our theta, the angle between the two lines. So now, we're saying the angle between the two lines is the difference of the angles that the lines make with the positive x-axis. And now we're saying, how can we use that? We've all the bits in place already for this, okay? Let's look at this, what this means. Tan theta is now obviously tan of alpha minus beta. You run immediately to your logbooks and you find the difference, the tan of the difference of two angles, okay? And you will get that it's tan alpha minus tan beta all over 1 plus tan alpha tan beta. We've already worked out that the tan is exactly the same as the slope of the line. So we can say that it's equal to now, just to be sure that you know, for L2 the slope equals M2, and the slope of this one is M1. All you need to know to get this far down the proof is that tan is just a fancy name for slope, which we normally call M from years back in second year mathematics and third year mathematics. And we just need to know where to find the tan of the difference of two angles in the logbooks. All very good so far. It's very easy to think that you've finished the proof now, but you haven't. And the reason you haven't finished it is we've actually only worked out information about this angle here. We haven't worked out information about the 180 minus theta. Now, it's easy. Let's look at the tan of 180 minus theta. Using the exact same tan formula, you actually find out that it's equal to minus tan theta. In other words, just using that formula there. So then, depending on whichever angle you're dealing with, we can now say, because yes, I need to just mention one little thing to you. We made a decision, and you mustn't forget that we made a decision to call this angle here theta. We could have made the decision to call that angle there theta. So now we can say, oh, guess what? If we had used this small inside one, we've got a plus in our equation. And if we do, the other one, look across to the right, the other one is minus it. So the answer is, depending on which angle was called theta, it's going to be equal to plus or minus okay? That's the important thing. Now that means that you can actually go along and you can put absolute values around the equation, which means then you can leave all this out here. But fundamentally in the proof, you shouldn't forget that having named one of the angles between the lines theta and proceeded and got an answer, that you have to go back and look at the second one, which is the 180 minus theta, to get all the marks. The books tell you that these relationships help prove a number of things, and one of them is when two lines are perpendicular to each other, that the slope of one multiplied by the slope of the other is minus 1. It pops straight out of this equation. The next thing you meet in these chapters is a different version of working out the area of a triangle. Now, in the logbooks, there are 3 equations. You will find it in the areas and volumes section. There are 3 equations for the area of a triangle. None of them is this one. So it's very important that you do memorize this equation. Okay? What does that relate to? Okay. Unfortunately, one of the corners of your triangle has to coincide with the origin. So what do? What you do is you set up a translation. If you've got a triangle anywhere else. You just want to translate it. So for example, if we have one here and we're looking at those 3 points, that one, and that one, you can happily pick any of them and you translate it. We'll pick the lower one here. And you want to translate it to the origin so that it becomes 0, 0. We'll do one quick little example on this so you're clear on it. Now what that means is we have to translate the other points so that we still finish up with our triangle. But the good news is we've now moved our triangle so as one of the corners touches the origin and we can use our equation up here. So let's translate a point then. We have a point here and we'll just say it's 2, 5, and we translate it down to 1, 7. What happens? Again, remember, if you think in terms of slopey lines, your life gets harder. So think in terms of vertical and horizontal lines. What happened? Sorry, this should be 7, 1. What happened to the x? The x value was 2. It's become 7. So it's increased by 5. What's happened to the y values? It went from 5 down to 1, so it's gone down -4. So the translation we have for this point is where the x value increased 5, the y value went down 4. Once we've found the translation for any corner of a triangle that brings it to the origin, the exact same translation will work on the other points. If I had to bring several more points under the same translation, all I'll do with any of those points for this translation we're looking at here is add 5 to the x and take 4 away from the y's. So it's a very fast process. And once you've done that, you can now use the equation that we have here. One of the two standard equations for the straight line is the one that we've already looked at. That's the slope. And this c value is where it meets the y-axis. The second equation is now you might ask yourself, where did that second equation come from? And it's very easy. You've been playing with it for several years. It's the definition or the equation for the slope of a line. If we say 2 points, one is xy and the other is x1, y1, the slope is m, and that's now going to be y minus y1 all over x minus x1. Looks familiar? And if I just multiply across by what's underneath the line here, by this bit, we now find that y minus y1 is equal to x minus x1 by m. That's all it is. The second equation for the straight line is just a reworking of a simple equation for slope. Let's peep at this top equation here. We know that the free number here is the intercept with the y-axis. What we need to find out quickly, just so as to know it for our own mind, is what's the value when it hits the x-axis? Well, on the x-axis y is 0, so we can say 0 equals mx plus c. That implies the x is equal to minus c over m. It's well worth remembering that because it does come up. It comes up in quite a number of questions. Now, one of my favourite little pieces is coming up. It's concurrent lines. Now, I know I mentioned in the first week, which was the yappy kind of one, where we talk about general little things that help you. And I was saying that multiplying anything by 1 doesn't change it, but it can actually help you solve problems when you use it in the form of a divided by a, where a is not 0. And the other thing was where adding 0 can help you. And in that case, it's an a minus an a. An example is in the proof by first principles for the product rule in calculus. There's a very odd one coming up here. To solve a particular problem, we're going to add 0 to 0 and get 0. And it actually solves a problem for us. It's very nice. Obviously, it doesn't really look like that's what you're doing, but in reality it is what you're doing. What are concurrent lines? Those two lines cross at a point, so they're concurrent. We could look for another line, any other line, crossing at the same point. Now, the important thing here is, if you don't learn this little piece, you could say, well, I don't have to worry, because if I work out where the two first lines cross, get the value of it, then I can go and substitute in that the coordinates for that crossover point, and then I can solve the problem for the third line. That would be grand if these questions were generally set up where you had a nice easy crossover point like 2, 3, but they're often set up in a fashion where you get a complicated one. It could be expressed as a decimal point or a serious rational number, like it could be 31 over 97, for example, for the x, and something equally unsavory for the y side. So what are we supposed to do here? And there's a trick. Now, the concurrent lines formula, we can name our lines. Let's say L1, and we'll name the other one L2. Now, our lines are normally written, as we have already seen, as an A1x plus B1y plus C1. We're just using the little letter, or the little number 1 here, so that we know that this A belongs to line 1. Okay? And likewise, we can say that L2 is equal to A2x plus B2y plus C2. Now, in all cases, these lines are equal to 0. For example, you could have 7y plus 2x minus 3 equals 0. So these two lines, L1 is 0 and L2 is 0. And the trick we're going to play is L1 plus a number multiplying into L2 equals 0. Now, we do know that any number multiplied by 0 is 0, so technically what we're doing is 0 plus 0 equals 0. And strangely enough, we can get a result out of this. Now, let's introduce you to a character, this guy here. That guy is lambda. Again, from our Greek tradition in mathematics, we're calling it lambda. It just means a number. It's a name. Now, you could call this Frederick for all I care. It's just a name. The important thing is, it's yet another example of using a name to identify and play with something that we haven't yet worked out what it is. We don't know what value the lambda will have, but we'll work that out afterwards. In the meantime, lambda will be like an avatar. It'll do what we want, the secret number we don't know, what we'd love to do with that particular number to get an answer. So we'll use a name, we'll use an avatar for it. I'll just straightforward apply the example that's given in the book here, because this is very simple, and once you see one example, it's all that is required for you to know what to do with it. If we have two lines, and we'll call that L1 for argument's sake, and we now have 7x minus 9y plus 7 equal to L2, and we're asked to find another line that has the same crossing point as these two, that they are concurrent. We need one more piece of information, something else about the other line, and it can be that it also contains a point 3,5, they might say to you, or they might, as in the case of example 2 in Aidan's book, it might say that the new line has a slope of 5/2. So you say, what do you do? Well, the easy thing to do is you set up an equation with lambda. And now we just put all the x bits together and all the y bits together and the free bits together. So we will get and what we're looking for is a particular one. There's a whole infinite number of equations of straight lines that we can get from this, depending on the infinite number of possibilities for lambda. But we're looking for a particular one, and the one we want is the one with a given slope. Now remember that when we have ax plus by plus c equal to 0, that we bring it, that equation would have been brought, and remember there's a big long one here, we don't want to do all the maths on that one, so you go across to the right hand side and you pick the nice little simple one that you know already, so that you can proceed, and we'll say, okay, by equals minus ax minus c. That implies we're saying y equals minus a over bx minus c over b, and we know that when we bring the equation in the form of one single y equal to something, that's the slope. So what we can say now is, in this line here, or this equation for all these infinite number of lines, we can know the slope. It's going to be minus the number multiplying into the x, that number, divided by that number. So we can say m is equal to minus outside of and that we know is equal to 5/2, because that's what we were given. Now the nice news is we have a simple little equation with only one unknown called lambda, so we can solve it, and having solved it we will just go back up to this line again and we'll use the value of lambda, and we get an equation of a line which will be the nice thing about this is the level of mathematics is just down into multiplication, addition, okay, division. It's not hard, leaving cert maths. This is a very powerful little tool. This tool is almost identical to the tool for working out common tangents and common chords and circles, which we'll be getting to in the next class. So remember that, okay? One of the other things that we have to play with has to do with the locus of something. Locus is just a nice fancy name, and the fancy name has to do with it's a rule, and this rule means that some things belong to the club and other things don't belong to the club. The locus comes up in the circle, but because it was dealt with first in the line, you find a proper and good definition in the books, generally in the line chapter but not in the circle chapter. So remember that there's a tie across in this. You will also find that the method is virtually the same in both. Now, there's only one trick to this. For example, the one given for the line would say, if I've got a point P, what we can say is the length from P to another point A is equal to the length from P to a line to a point B. Okay? So P across to this point A, find that length, and it's going to be exactly the same as P across to the line B. And we're looking for all possibilities of P. Well, the obvious thing to do is you let P equal to X, Y. And when you do that, and when we know what A and B are, and for example, just in the case given in the example here, where A is 1 minus 1 and B is 5, 3, we can now set up our equation here, which is just our distance formula. Okay, so we can say the square root of x minus 1 squared we know that is equal to, I'm just copying the top line here, I'm just putting it in different terms, it's equal to the square root of x minus 5 this is putting into algebra what this little half of the definition of the locus is telling us, in a sense of just saying the distance from P to A. Now obviously the same thing is true here. That is just being reflected in this. All we've got to do is square both sides and we can solve. Okay? Now when you solve, you'll find an expression, one equation, obviously, because that's all we're dealing with here, and that one equation will have an x in it, a y in it, and a constant, and as it turns out it'll finish up x plus y equal to 4, and that, as you know, is the equation of a straight line. So the solution to this locus problem here, the set of all points P that solve this little rule, is in fact a straight line. What you will notice in the circle is something almost exactly the same as this, but the answer that comes out of it is, not surprisingly, a circle. The last thing that we need to cover is the perpendicular distance. The proof of the perpendicular distance equation is something that can also be examined and can be asked in the Leaving Cert. Okay, so it's an important one. But the good news is it's the last little thing you have to do for the chapter. Okay, what is the formula? We'll just call it D for the moment. Clearly it's in the logbooks, but its proof isn't in the logbooks. And this isn't hard. The things you've learnt already from the line come in very quickly here to prove this equation. Okay? There are just 3 steps to this. So let's look at what we want here. we're trying to find out that distance, the perpendicular distance. What things do we know? Well, first thing we can work out really quickly will be that angle there, which we can call theta. Not very adventurous, but it is traditional. So we're saying, theta. The first thing we need is we need an expression for sine of theta. What do we know? This should be very familiar to you. The slope m, which happens to be tan of theta, is minus a over b, where that's the a and that's the b we're talking about, okay? So we're saying the slope of the line is the tan of the theta, okay? So now we're saying that's tan of theta. So what we want is something to do with sine of theta, so we set up a little diagram. By the way, you use this methodology in trigonometry, so it's well worth seeing it now because you're going to have to deal with it again. It also comes up a lot in the calculus questions, because when you've got inverse trigonometric functions, you use this method, and if you use this method well, you can actually convert some questions that have been asked in the last 10 years, part C questions, you can convert them into a dawdly part A question. So it's well worthwhile remembering this, okay? What we're saying when we talk about a slope is, we were saying slope is the difference in the y all over the difference in the x. And what we're saying is, okay, in this case here, this is my angle theta. And we're saying, okay, tan is minus a over the b. It's the opposite over the adjacent. That's the tan. Good old Pythagoras tells us that this line here is a squared plus b squared. So sine theta equals plus or minus that's our first equation, and you're 1/3 of the way down to proving this big equation up here. Now, what's the next thing that we need to know? See this r length here? Well, we're going to call it r because we like naming things. We're saying x1, y1 here, and r is horizontal, okay, because that's a line parallel to the x-axis, and we can say, the y value will be the same, but over here, what's the x value? Well, it's x1 minus r is the x value. So we're able to say, grand, this location here, I know that point, okay? And we'll call that point S. So now we're saying S is this point x1 minus r y1. So what we can have now a very small step brings you to a second point where you've expressed r just in terms of numbers you know already, because that's always the trick in these things. It's ax1 plus by1 plus c just divided by an a. Now life gets interesting now, because obviously we had our theta down here, our theta is also here, and what you will notice is we have a right angle triangle. Obviously this is our right angle, and we can start talking now in terms of dealing with p. Now I'm going to remove part of this now. I'll remove this equation piece here. I want us to draw a little drawing, and it's a one that you can use when you're dealing with parametric versions of lines. It comes into complex numbers, it comes into calculus and several other things. I just need you to see this. Here's a little diagram. Right angle. We'll say this whole length up here, we'll just say for the moment is r. And we're trying to work out, for example, that length and that length. The trick is the same old little trick that we did with the unit circle from trigonometry. We're saying, what if we only went out 1 unit here, just 1 unit, that length is 1. I can drop a line here. Now that's theta. From our unit circle in trigonometry, I know that I've got cos theta here and I've got sine theta here. What I know from similar triangles from junior cert is these two triangles are similar because they both have the theta. You have a right angle here the same way as you have a right angle in here, and that means that the third angle, this one and that one, they must be the same. These are similar triangles. Now all we have to do is to find a given side in each of the triangles that hold the same respective position and get the ratio. And the ratio is provided on the top line. You've got an r up along here, that length is r, and you've got a 1. So I know the ratio is r is to 1. That means similar sides will give me the same type of an answer. So I have a sine theta over here in the vertical side, so that means this over here is r sine theta, and this one down here is r cos theta. Just based on similar triangles, we're in a situation where we're able to say now that the long base side of that triangle is r cos and the other one is r sine. If we look across to our diagram on the right hand side, this one over here, we're looking at the right angle is there, that's the one we've been dealing with, and we're looking at what are our relationships, okay? And what we will say based on that is that P, which is r sine theta, and we now have an expression for two things already. We know an expression for sine theta. It was the first thing we worked out. This is it here. We also have an expression for r, that's it down there, and we just multiply one by the other and we get the equation that we're looking for, which is remember, there's just 3 little steps in this, but you do need to have a knowledge of basic trigonometry for this. Fundamentally, you need to know the tan is slope. You also just need to understand about similar triangles so that you can come up with an r sine and an r cos and all that kind of stuff, okay? And you get your expression for the perpendicular distance, which is going to be called P over here. We've been looking all along for that. And we are very happy to find that it is r sine theta, because we've worked out r and we've worked out sine theta. Now, it's a funny little chapter because there's about 4 separate bits in it, which have the concepts of them. We've just gone through the concepts of them. Other chapters seem to run better than this particular one. This seems definitely broken in and compartmentalized. Having said that, it is one of the most important chapters, because if you understand this, you already have almost everything you need to know for first principles calculus. You already have a good understanding of relationships that leads you into trigonometry, and you get help for complex numbers, the second half of complex numbers. There's also an equation here which is almost identical to one in vectors, this one here, which is the angle between 2 lines. It's very hard to express to you how important this little chapter is, and the one that we'll be covering next, which is the geometry of the circle. Okay, see you at the next one.